The first set of inverse functions that we're going to find the derivative of include the inverse trig functions like arcsine, arccosine, arctangent. Prior to that, though, let's review some inverse properties from algebra, starting with the definition, which has to do with composition. So you may remember that whenever you take an inverse function and you compose it with the original function, you're supposed to get the original input back. This is why we say that inverses, they undo each other. You're going to stick something into the f function. It's going to do something to it. And then if you plug that answer into the inverse, it's going to undo all of those things that f did, giving you the original input back. Here's a very simple example. If I take the square root of 5 and I square it, I get 5 back, right? My original input is 5 into the square root function. The square root function is going to do something to it, and then the squaring is going to undo what the square rooting function did as inverses. Now, another complication that happens with inverse functions is the fact that there is a domain and a range kind of limitation there. And the reason why is because the x's and y's switch. So the domain and range is also going to swap places. Whatever the range is for the original function, that becomes the domain of the inverse function. But sometimes it doesn't always work. It doesn't always work perfectly. Like, for example, when we think of a parabola, this is the example that we were just talking about here, its inverse function should actually be a sideways parabola. The problem with that is that, it's not a function, so we get rid of half of it. We get rid of this part. We also get rid of, let's say, this part over here. We have to get rid of some of the functions so the inverse is actually a function, right? So that's one of the limitations that happen with inverses. Same thing is going to happen with inverse trig. Let's do a little graphing and calculator investigation here. I'm going to pull up Desmos as I do. Okay, and let's graph a couple of functions. I'm going to graph as my first function. I'm going to do ones that we know are inverses before even some trig stuff. Let's do e to the x and the natural log of x, right? So f of x, and then let's make that equal to e to the x. All right, there's my graph of that. As I expected, let's do g of x for the second one. And then let's make that equal to the natural log as the inverse of that thing, functions. What is this? Miscellaneous inverse and then x. And then there's that function. And as we mentioned before, when you switch the x and the y, that reflects your graph across the line y equals x. And now let's do a composition. Let's take that natural log function and let's stick it into the e to the x function. Right, we're going to do a composition. I'm going to call that one h of x, I guess. H of x, x equals, let's put the g of x inside of the f of x. G composed with f of x. Yeah, that's what I want to do. No, not times it. Of it. All right, so this is exactly what we expected, right? We get, remember when we do the composition, as I showed you before, you're supposed to get x back. So it's like you have the equation y equals x. Everything works out exactly as expected. But let me switch the order of those two things, and let's see what happens. Maybe I call this one, I don't know, k of x. I'm going to switch the order of them, is equal to, and then let's put the this time e to the x inside of the natural log function. Okay, so this one is going to be f of x is on the outside, is that right? Oh, I see what I did here before. I told you I was putting the natural log inside of the e to the x, but I didn't do that, did I? I put the e to the x inside of the natural log. Okay, anyway, so yeah, let's reverse that process. Let's put the natural log, so that's g of x inside of f of x. So f of x is on the outside. F composed with g, parentheses x. There we go. All right, so now it's not easy to see because I got too much stuff on the screen, so I'm going to get rid of this green one. And look what happened. What the heck? We don't get the whole entire line y equals x. Why does that happen? Here, let me take a picture of this, bring this into notability, and see if I can actually... Oh, yeah, okay, fine. I'll save that to photos. Let's see if I can mark this thing up. There we go, perfect. And let's see if we can wrap our heads around what the heck just happened here. Okay, so for this k of x function, basically what I just did was y is equal to, f of x is the e to the x, so e to the natural log of x is what I just did. And we always talk about, hey, these things cancel each other out, and they give me my original input back of x, but not entirely. And the reason why is because the input here goes into the natural log of x. And there's a limitation. The domain for the natural log of x is from 0 to infinity. You can't plug in 0 because that's undefined, and you can't plug in any negative numbers, which means for the composition, this is going to be the domain, which is why you don't get anything over here, because you don't get to stick anything over there. And then whenever we stick those numbers into the e of x function, e to the 0, I don't actually get to do, but it would be 1, and then everything after that, if I plug in any numbers after that. And that's why I'm only getting the stuff over here in quadrant 1. All right? So now it's going to get a little bit more complicated with some trig stuff. Okay. All right, then, so let's go back over here, and let's maybe make a new blank graph, and let's do sine. Yeah, let's do sine. So we'll do f of x for sine. Why do you do that, Desmos? Equals sine of x. All right, there's my sine of x function as anticipated. And then let's do the inverse as g of x. And I do have a function for that. It's up in here. Oh, yeah, there we go, of x. And look, it's not the entire graph flipped over the line y equals x. The reason why that is the case, of course, is that if that happened, there in no kind of way would the inverse be a function. So we have to take only part of the original domain. Let me again pull this thing into Notability so we can mark this thing up right here. Right about there. Yep. Okay, so once again. So what happens here for sine is that you only get a certain interval. We have to get rid of the part of the domain of the original function so that the inverse is also a function. You had to do that back up here on the squaring function. We had to get rid of all the negatives so that the inverse, as the square root, is only the positive side, and you don't have to worry about the negative side, and that the inverse is a function. Got to do the same thing. So what we have decided to do is go from this point to that point. What are those numbers? That is negative pi over 2 to positive pi over 2. Over that interval, sine of x is a one-to-one function. Every input has one output. Every output has one input. So when we take its derivative, when we take its inverse, then the inverse is guaranteed to be a function. Okay, so there's that part. And then the next part is let's go ahead and graph. Let's go ahead and graph some inverses together, so as a composition, just like we did to the e to the x function. So let's say, for example, that I want to let's put like h of x is going to be equal to, what order am I going to do this first one in? Let's do the inverse of sine. Let's maybe put g of x inside of f of x. Does that sound good? Okay, so then that's what I'll do. F composed with g of x. Okay, so I've got too many graphs crowding the space here, so let me kind of hide a couple of those. And notice that on this one, we're only going to go from, what the heck, from -1 to 1 on these graphs? Why does that happen? From -1 to 1. It looks like I'm going to have to pull some of this stuff in again. Come back over here and write on the screen. There's not enough space. Let's add some more. Okay. All right. The function that I just graphed here was this. Y is equal to, f is on the outside, which is the sine function. On the inside is the inverse sine. And sure, yeah, those things are supposed to cancel out and give me y equals x as the definition of inverses. But there is a domain and range limitation, and it has to do with this inverse sine that's inside here. Well, the inverse sine, as a graph, as a function, what is the input? Remember that you can stick anything in for sine, original sine, as you want to, but as far as what it outputs is only ever going to be anything from -1 to 1. So, right, if I come back over here to my little graph and just look at this function by itself. No, just that one by itself, yeah. Try again. There we go. You only get to stick stuff in. Its domain is from -1 to +1, right? So that's the original domain for this function. From -1 to +1. Wait. I'm on this. There we go. This is better. Okay. And then it's going to output something. It's going to output something, and it'll always be a number from -π/2 to +π/2. And if I were to take, let's say, the sine of -π/2, I'd get -1. If I take the sine of +π/2, I get +1. This is the reason why. This is the only part of the graph that we get. All right, let's, yeah, I hope you're ready for this. I don't know if you've ever seen this before, but we're about to do it in the opposite order here. Let's see the craziness that is about to transpire. Okay, and then I'll let you see if you can figure out why this actually happens, and then we'll do some other calculator activity, I think. So I'm going to do g of x on the outside this time. So g composed with the f of x. Oh, wait a minute. Oh, you can already see what's going on here, but I forgot to name that function. I'll call it k of x. There we go. What? Look at that. What the heck? So we certainly don't get just y equals x in this case. We get something far stranger. Why is that happening? Why is that happening? So what I want you to do is, because I'm about to end the video here, it's long enough, I want you to think about why that is happening. Why is that purple graph? It looks basically like the sine graph, except for, you know, with straight pieces, like linear pieces, instead of with nice smooth curves like sine usually has. And then we'll talk about it in the next video why that happens.